Hey everyone, Praveen this side. I hope you guys are doing great. So today we are going to solve the problem search in a sorted matrix. Again searching in a sorted matrix variation, which is a medium level problem. But trust me guys, we are going to understand this problem in such a way that this medium level problem will become very easy. Okay. So let's read the problem description. The problem says given a strictly sorted 2D matrix mat of size n cross m and a number x. So we have been given a matrix of size n cross m and a number x, which is nothing but the target. Now we need to find whether the number x is present in the matrix or not. It is very self-explanatory, right? That we need to find this number x is present in the matrix or not, right? Now there's a note point here saying in a strictly sorted matrix, each row is sorted in strictly increasing order and the first element of the ith row where I is not equals to 0 is greater than the last element of I minus 1th row. So here we have been given the definition of strictly increasing order in terms of matrices. Now let's suppose we have a matrix that is A, B, C, D, E, F, G, H, I. Okay. Now what this note point is saying that the element at the ith row, let's suppose this is the ith row. Okay. So this is the ith row. So the first element of the ith row where I is not equals to 0. So this element will always be greater than the last element of the I minus 1th row, which is nothing but this element will always be greater than this element. Where if it is ith row, it will be I minus 1th row, right? So C will always be greater than D. G will always be greater than F, which is nothing but matrix of ith row with element 0 will always be greater than matrix of I minus 1th row, the last column name. Let's suppose it be col. Okay. So this condition will always satisfy in every row. Okay. So this is the node point. And once we understand this node point, right, it will become very easy. Okay. But before that, let's understand the example to get more clarity. So let me rub this. Okay. So in the example 1, the matrix is 159, 14, 20, 21, 30, 34, 43, and the target is 14. Okay. So the output is true. Why? Because we can find this 14 at this position, right? So 14 is present in the matrix, so the output is true. Simple. And again, in the example 2, in this matrix, we need to find 42. Now, if we try to find 42, we don't find it here, neither here, nor here, right? So the output is false. Now, the same goes with the example 3, that we need to find 101. So, can we find it here? No. Can we find it here? Yes, we can find 101 here. So, the output is true. So the examples are very basic and pretty self-explanatory, right? Let's see the constraint first. So the constraint says n and m size will be between 1 and 1000. So the time complexity, the max time complexity it can achieve is still 10 to the power of 3 into 10 to the power of 3, which is nothing but 10 to the power of 6. So we need to solve this problem within n log n. Okay. Because 10 to the power of 6 operations can only be handled within n log n. If it even goes O of n square, I guess it will give TLE. Okay. And matrix of ij will be in the range 10 to the power of 9. So the numbers can be stored inside the integer. And the target value is also given in terms of integer. Okay. So with the constraints, we have assumed what can be the time complexity be. Okay. So we have understood everything here, right? So let's consider example 1 as reference and we'll try to find few observations from it. So this is the matrix and this is the target that we need to find. So what is the brute force approach that we can apply in this problem? Simply iterating in each element in this matrix and constantly checking whether the element matches with this element or not. That is, we'll go with for this element, then this, then this, then this, then this, then this, and so on, right? And as soon as whenever we find that particular row element at the column position matches with this element, we return it as true. And after searching in the whole matrix, even if we don't find this element, we'll return it as false. Simple, right? Now, how can we achieve this? Let's suppose the matrix size be n cross m, where we have n rows and m columns. So we'll be using two nested for loops to iterate in the matrix. One for iterating in row, which will be starting from 0 till n minus 1, right? And another for loop which for column, which will be starting from 0 till n minus 1. Okay. And inside we'll be checking whether matrix of row column is equals to x. If it is the case, we'll simply return true. Yeah, return true. Okay, but even after all the execution inside this for loop, we never find this element, then outside this loop, we can simply return it as false. So this is the brute force approach, right? That hits in our brain as soon as we see this problem. Now, what will be the time complexity for this approach? As you can clearly see, we are using two for loops, one of size n and another of size m. Sorry, here it should be m. It should be m because we have taken n cross m size, right? So the time complexity will be O of n cross m. Simple. And what will be the space complexity? Here, we didn't use any additional data structure. We are just traversing in the existing matrix, right? So the space complexity will be O of 1. So with this time complexity, will this problem be submitted? I have personally tried to submit this problem and somehow it got submitted. As I said, the time constraint should be less than O of n log n, but with O of n square too, it got submitted. Now I don't know what is the reason, but with this approach, you can submit your problem. But our intention is not to be satisfied with this brute force approach, right? If we see any further optimization in this problem, we need to optimize it as optimal as possible. So let's see what will be the optimal approach for this problem. So in the problem description, it is clearly said that each row is sorted in strictly increasing order, right? So if we see the visual representation, if we flatten this matrix, how does it look like?
40 to the 1, then 5, then 9, 14, 20, 21, 30, 34, 40. Right.
So this is the array that we generated. And if we properly do the indexing, it will be 0, 1, 2, 3, 4, 5, 6, 7, 8. Now, finding this target inside this 1D array is very easy, right? We can simply use binary search. And I guess most of you guys know how binary search works, right? And if you don't, I'll drop a link to my video where I clearly explain how binary search works. But I'm assuming most of you guys know how to use binary search, especially in 1D array, right? So for the binary search, what we'll do, we'll take left pointer, we'll take right pointer, we'll calculate mid with this left and right pointer, and we'll try to match this target element with the mid pointers element. And if it is the case, then we'll return true. But if it is less than, we'll move our left pointer from here till here. That is nothing but the one position ahead from mid. But if it is not the case, we'll shrink our size by bringing right pointer to one step behind of the mid pointer. So this is the basic functionality of binary search, right? So applying binary search in 1D array is very easy, right? But why can't we apply the same binary search in two-dimensional array? If we are able to apply it in one-dimensional array, there must be some path, some way that we can apply the same binary search in the two-dimensional array, right? So how can we do that? So here I have written the array neatly so that we can compare both matrix and array and the relationship between their indices both in 1D and 2D. Okay. So let's take both array and matrix in terms of indices. Okay. So if you see 1 in array, 1 is present at index 0, but in matrix it's at 0 comma 0. Okay. So I'll write in array it's 0 and in matrix it's 0 comma 0. And for 5 it is at index 1 and here at index 0 comma 1. Okay. So it is at 1 and it is at 0 comma 1. Now similarly for 9 it is at 2, it is at 0 comma 2. Let me fill everything and I'll be back. So here I have noted the indices of 1D array with respect to 2D array. Okay. Now if we look at the random index, let's suppose 5. At index 5, we have 21. Okay. And similarly, the mapped index, which is at 1 comma 2, we have 21. Simple. So these are mapping properly, right? Now, as we have discussed, applying binary search on 1D arrays is very easy. So in the similar way, it will be very nice, right, that we apply binary search in matrix and get the time complexity of O of log n, right? So what was the main constraint that we were not able to apply binary search in this matrix? Because it is in two-dimensional, right? Because of that, we got feared. Like, how can we even think of applying binary search in 2D matrix? For 1D, it is clear, right? So because of that, we have drawn the mapping. So if we use the conventional binary search and with this mapping, if we try to get the indices, won't it be very easy? So what we'll do is we'll use the standard binary search. We'll take both left pointer, right pointer, mid pointer, okay. And while doing that, we'll get this 1D array index. Now the main concern is to convert this 1D array indices to this matrix indices, right? How can we do that? So it is not intuitive, but it is a trick with which not only in this problem wherever you need to get the indices of 2D array in terms of 1D array, you can use this trick, which is nothing but, suppose if the matrix size is n cross m, right? So how to get row? To get the row, what we'll do is we'll take I by m, where m is column size and where I is the index of the 1D array. Okay. And similarly, to get the column, we'll do I modulo m. And again, I is the index of 1D array. Okay. I'll note it down here. I is the index of 1D array. Okay. Now to prove that we get row and column with this index, let's take a random index. Let's take 7. Okay. So here we'll take 7. Okay. Now what is m? Here we can see m size is 3. That is every row has 3 columns. Okay. So the m size is 3. So if we do 7 by 3, what will be the answer? It will be 2, right? And similarly, if we do 7 modulo 3, what will get? We'll get 1. So if I write in plain division that we used to do in schools, that is if we do 3 and 7, 3 twos are 6 and the remainder is 1. So the division will give us quotient and the modulo will give us remainder, right? So we achieved the same 7 by 3, which is 2, and 7 modulo 3, which is 1, right? So if we look properly at 7th index, we have value 34. And similarly, if we try to look at second row and at first column, what we have? So in the second row at the first column, we have 34, right? So we have proved whatever we said, right? So this is the very important formula. Remember it, guys. This formula you can use in many questions, and I personally have used this formula in many questions. Okay. So the main concern of not using binary search in matrix is gone, right? With this formula, we'll treat our matrix as normal array and we'll try to find mid. Now, whatever mid value we'll get, that will be acting as index, right? So from that mid index, we'll retrieve both row and column. Simple, right? Now, okay, we got to know how row and column can be calculated, but what will be the search space? Like, where do we start our left and right pointers? So if we see clearly, we have at 0th index, we'll place our left pointer, and at the 8th index, we'll place our right pointer. But we have been given a matrix. How can we get 8? It's simple. Right? This n cross m says how many elements are present in this matrix, right? So if we do 3 cross 3, we'll get 9. But we want in terms of index, and index starts from 0. So we need to do minus 1. So 9 minus 1 will be 8. So the right pointer will be n into m minus 1. Okay. And left pointer will be basic 0. Simple. So we'll treat this whole matrix as a single 1D array and we'll apply our binary search. So I hope we have learned a good number of observation points from it, right? So let's consider this matrix and keep these points in mind, and let's try to search 14 from this matrix. Okay. So here our low is 0 and high is 8. Why? Because we have been given 3 cross 3 array. So 3 cross 3 will be 9, 9 minus 1 will be 8. The formula that I have written here, right? So let's try to apply binary search on it. So low is 0, high is 8. So what will be the mid? Mid will be 0 plus 8 by 2, which is nothing but 8 by 2, which is 4. So we have got 4 as the mid. Now how to calculate the row and column? As we already know, row will be mid by m and column will be mid modulo m, right? Let me move this down a bit so that the values can be written properly. Let's calculate both row and column. For this, we'll do the normal division, 3 divided by 4, right? So 3 ones are 3 and we got a remainder of 1. So row will be 1, okay? So the row is 1 and the column is 1, which is nothing but the remainder. So we got both row and column as 1 and 1. So in the matrix, if we search 1 and 1, what we have? We had 20, right? So we'll match whether this 20 is matching with this 14. No. But we see that 14 is less than 20, right? So when number is less than the mid value, what do? We bring the right pointer to the mid plus 1, right? High will be 4 minus 1, which is nothing but 3. Simple. Okay. So let's erase this everything again. This will be erased, this will be erased, this will be erased, and this will be erased. Okay. Now our low is 0, high is 3. Now let's calculate the mid again. So it is 0 plus 3 by 2, which is nothing but 1 again. Okay. So our mid is 1. Now to calculate both row and column, let's take the division. So it is 3 with 1. So 3 zeros are 0 and we got 1 as remain. So row will be 0 and the column will be 1. Right. Now if we try to check 0 comma 1 inside this matrix, where does it lie? Now at row 0 and column 1, what is the value we have? We have 5, right? So we'll check whether 5 is equals to 14. No, 5 is not equals to 14. But 14 is greater than 5. So our target value is greater than the mid plus value. So what we'll do? We'll bring our low pointer to mid plus 1. Now here mid is 1. So mid plus 1 will be 2. So we'll update our low with 2. Okay. And let's reset everything. So this will be erased, this will be erased, this will be erased, and this will be erased. Again, we'll try to calculate mid. So mid will be 2 plus 3 by 2, which is nothing but 5 by 2, which is nothing but 2. Okay. So we got the mid as 2. Now what will be the row and column? So we need to divide 2 with 3. So 3 zeros are 0. So the remainder is 2. So again we got the row as 0 but column as 2. Okay. So we'll check at 0 comma 2, which is nothing but this. So we'll check whether 9 is equals to 14. No, 9 is not equals to 14. But 14 is greater than 9, right? So we'll update our low pointer with mid plus 1. Okay. So it will be 3. Simple. I'm pacing fast a bit because we have got the hang of it, right? So let's erase this. Let's erase this, and this. Okay. Now our low is 3 and high is 3. So 3 plus 3 by 2 is 6 by 2, which is nothing but 3. So we have got our mid as 3. So let's divide our 3 with 3. So 3 ones are 3 and the remainder is 0. So the row is 1 and the column is 0. So we'll check at 1th row and 0th column, which is nothing but this, right? So we'll check 14 is equals to 14. Yes, 14 is equals to 14. So at this moment only, we can return it as true. Simple. But suppose we had 15 here. So 14 is not equals to 15. So what we'll do? 15 is greater than 14, right? So we'll update our mid pointer with mid plus 1, which is nothing but low will become 3 plus 1. So low will become 4. Okay. Now here, as you can see, low is become greater than high, which is the base case of the binary search, right? So at this point only, we need to break out of the loop. So when we break the loop and not found this element, we can simply return it as false. Simple. So we have used the normal binary search in 2D array, right? Smartly, just with taking care of calculating row and column. Otherwise, everything is similar, right? We have low, high, mid, but this is the extra thing that we did. So the diagram is clear, I guess. If the diagram is not clear, take few other examples. Try to solve it on your own. You will definitely get it. Okay. Now, with these observations, let's jump into the code. So here's the code in C++, although the logic remains same irrespective of programming languages. So the function name is search matrix and we have been given matrix and x. So firstly, I have taken matrix size and stored it in n, which is row, and matrix of 0 dot size and stored it in m, which is nothing but columns. So I have initialized two pointers, left and right, where left is 0 and right is n into m minus 1, and I'm running this loop while left is less than or equals to right. So inside I'm calculating the mid by left plus right minus left by 2. Now why did I calculate this mid like this? Please comment it down. I want to know from you guys. So after calculating the mid, I'm calculating row and column. Row by mid by n and column by mid modulo m. Okay. And I'm checking whether the matrix at that row and at that column is equals to x. If it is, then return true. But the but if the value is less than x, then I am shifting my left pointer to mid plus 1, else shifting the right pointer to mid minus 1. So this piece of code is the basic binary search template, right? Just the extra thing that we are doing is calculating row and column and dealing with matrix, right? Apart from that, the code exactly looks like the standard binary search. So inside, we never hit this case where we need to return true and we have exited the loop. We can simply return it as false. So this is the basic code, right? Now, what will be the time complexity for this approach? Here, as we are discussing from the start that we are using binary search, so the time complexity will be O of log n, which is a huge optimization compared to our brute force approach where it was going to O of n square. And what will be the space complexity for this approach? Here, apart from using variables, we didn't use any extra space, right? So the space complexity will be O of 1. So I hope you guys like this video. If you guys really did, then please like, share and subscribe to my channel. Your subscribing to my channel will really motivate me to make more quality content videos. If you have any doubt at any point, please comment it down so that I can respond to it as quickly as possible. And if you have any feedback for my teaching, please comment it down too so that I can improve on that. So let's meet you guys in tomorrow's video solving any other coding problem. Till then, stay safe, stay happy, and peace.